Have you ever wondered if we could break the ultimate speed limit of the universe, the speed of light? This isn't just some arbitrary speed limit put in place by the cosmic police. No, this is a fundamental aspect of our universe, deeply rooted in Einstein's theory of relativity. To understand why the speed of light is considered the absolute maximum, we need to delve a little into the world of relativity. According to Einstein, as an object moves faster, its mass increases. This is not a problem if you're moving at ordinary speeds. But as you approach the speed of light, your mass would become so great that it would require an infinite amount of energy to continue accelerating. And since we don't have an infinite source of energy, reaching, let alone surpassing, the speed of light is deemed impossible under traditional physics. But it's not just about energy. Time, that ever-ticking clock, also plays a role. As you approach the speed of light, time slows down. If you could somehow reach the speed of light, and remember, physics says you can't, time would stop altogether. And if you managed to go faster, you'd end up in the realm of time travel, going back in time, which opens up a whole new can of paradoxical worms. So with these constraints, it seems like our dreams of zipping across the universe faster than light are just that, dreams. The speed of light, roughly 300,000 kilometers per second, is the cosmic speed limit, an unbreakable barrier under the laws of physics as we understand them today. But what if we could bypass this cosmic speed limit? Let's delve into the theories that suggest we might. Because as they say, rules are made to be broken. And in the next scenes, we'll explore some theoretical concepts that could potentially allow us to cheat the universe, to sidestep the speed limit, and open up the cosmos to faster than light travel. So buckle up, it's going to be a wild ride through the frontiers of theoretical physics. Imagine if you could step into a portal and come out in a completely different part of the universe. Welcome to the world of wormholes. Wormholes, in theory, are fascinating constructs. They're often described as bridges, or rather, shortcuts through the fabric of spacetime. If we picture spacetime as a two-dimensional sheet, a wormhole would be like a tunnel connecting 2 points on this sheet, potentially allowing for travel distances that are much shorter than the traditional route through space. But as with anything that sounds too good to be true, there are significant challenges to the existence and use of wormholes. For starters, their stability is a major concern. Wormholes, according to current understanding, are incredibly unstable and could collapse suddenly, which would be a rather unfortunate event for any intrepid space traveler caught inside. And then there's the matter of exotic matter. Exotic matter, unlike the ordinary matter we're familiar with, is theorized to have negative energy density. This is important because such matter could, potentially, keep a wormhole open. But the existence of exotic matter is purely hypothetical at this point. We've yet to discover any real evidence of it in our universe. So, while the idea of stepping into a portal and coming out light years away is certainly intriguing, wormholes remain, for now, a theoretical concept. Practical, usable wormholes may be beyond our reach, but don't lose heart just yet. Wormholes aren't the only game in town when it comes to faster-than-light travel theories. What if we didn't have to move through space, but could instead move space itself? This is the idea behind warp drives. Now you might be thinking, warp drives? Like in Star Trek? Well, yes and no. The concept is similar, but actual theoretical physics is a bit more complicated than science fiction. Warp drives involve bending or warping space-time, the four-dimensional fabric of our universe, to allow a spacecraft to effectively travel faster than light. Let's imagine for a moment a piece of paper representing space-time. If we want to get from one side of the paper to the other, we could walk across it, which would take some time. But what if we could simply fold the paper, bringing the two sides together? We'd technically still be moving slower than light, but because we've bent space-time itself, we've taken a shortcut. A specific example of this concept is the Alcubierre Drive, proposed by Mexican physicist Miguel Alcubierre. The Alcubierre Drive proposes the idea of a bubble of space-time moving faster than light, with a spacecraft safely inside. The space in front of the spacecraft would contract, while the space behind it would expand, creating a wave of space-time that the spacecraft would ride. Yet, as exciting as warp drives sound, they're not without their own set of challenges. The energy requirements alone are enormous. and there are still many questions about how to create and control such a warp bubble. Warp drives are another fascinating concept, but they also come with their own set of challenges. Did you know that particles can be instantaneously connected, no matter how far apart they are? This is quantum entanglement. Quantum entanglement is a peculiar, yet fascinating phenomenon that exists in the quantum world. It's like an invisible thread that ties two particles together, creating a cosmic dance where changes to one particle instantaneously affect the other. This connection persists regardless of the distance separating them, whether they're a meter apart or on opposite ends of the universe. Now let's delve a bit deeper into this concept. Imagine two entangled particles, each spinning in a particular direction. If the spin of one changes, the other will immediately mirror this change. This spooky action at a distance, as Einstein famously dubbed it, happens faster than the speed of light, defying our conventional understanding of time and space. You might be thinking, could this be a potential avenue for faster-than-light communication? It's a tantalizing thought indeed. By manipulating the state of one particle, we could, in theory, instantly transmit information to its entangled partner, no matter how far away it is. However, it's crucial to note that this is a topic of ongoing debate among physicists. The main challenge lies in the fact that the entanglement breaks when we measure or use the entangled particles, making it tricky to harness for practical communication. Quantum entanglement is a strange and wonderful aspect of the quantum world. But does it hold the key to faster-than-light travel? The jury is still out. What if there were particles that only moved faster than light? Meet the tachyons. In the realm of theoretical physics, tucked away in the corners of the hypothetical, reside tachyons. These are particles that, in theory, always move faster than light. The concept of tachyons brings a fascinating twist to our understanding of the universe. Picture this, a particle that not only races past light, but lives perpetually in the fast lane, never slowing down to the speed of light or below. It's a concept that sounds more science fiction than science fact. And yet, it has been seriously discussed within the scientific community. But the existence of tachyons presents some significant challenges. Firstly, they are purely theoretical. Despite numerous attempts, no direct evidence of tachyons has been found. They remain an elusive concept, a tantalizing possibility that we have yet to pin down in the empirical world. Secondly, tachyons could create paradoxes. If particles can move faster than light, then it might lead to violations of causality, the principle that cause comes before effect. This is because, from certain perspectives, tachyons could appear to move backward in time. The world of tachyons is a world of what-ifs. It's a world that challenges our understanding of the universe and the fundamental laws that govern it. While tachyons are an interesting concept, we have yet to find any evidence of their existence. But in the search for the extraordinary, who knows what we might discover? In a universe where energy is always positive, what would negative energy look like? Now that's a question to ponder on. Imagine energy as a cosmic currency. Positive energy is like spending that currency, creating matter, heat, light, and movement. But what about negative energy? It's like having a cosmic debt. The concept of negative energy is a strange one, and it's theoretically required for phenomena like wormholes and warp drives. But there's a catch. Negative energy defies the known laws of physics. It's like trying to subtract apples from an empty basket. It just doesn't make sense in our current understanding of the universe. In the world of quantum physics, however, negative energy is not entirely out of the question. Quantum fluctuations can, in theory, produce brief periods of negative energy. Yet, harnessing these fleeting moments of cosmic debt is a monumental challenge. Additionally, negative energy poses theoretical problems. Too much of it could destabilize the universe, causing a runaway effect that might erase everything in existence. It's a risk that even the most adventurous of physicists might be hesitant to take. So, while negative energy might be the key to unlock faster-than-light travel, it's a key that we're far from finding. Theoretical physics often walks a fine line between revolutionary ideas and flights of fancy. Negative energy is a fascinating concept, but it remains purely in the realm of theory. So can we ever expect to travel faster than light? A question that has intrigued scientists, authors, and dreamers alike for centuries. As we venture into the future, it's worth revisiting some of the theories we've explored today. First, we grappled with the speed limit of the universe, the speed of light. Overcoming this barrier is no easy task, and it has implications that could shatter our current understanding of physics. Yet, the pursuit of knowledge continues unabated. Next, we delved into the concept of shortcuts through space-time, or wormholes. These theoretical passages could potentially allow us to leapfrog vast cosmic distances in an instant. However, the stability of these wormholes and the energy required to keep them open pose significant challenges. We then explored the idea of bending space-time itself. Theoretical constructs like the Alcubierre Drive suggest we could warp the fabric of reality to move faster than light without actually breaking the speed limit. But again, the energy requirements are astronomical, and the practicality remains uncertain. We also considered the concept of quantum entanglement, or spooky action at a distance, which could potentially enable instantaneous communication across the cosmos. Yet how to harness this phenomenon for travel is still a mystery. Lastly, we looked at hypothetical particles that could travel faster than light, known as tachyons. If these elusive particles exist, they could revolutionize our understanding of the universe and potentially open up new pathways for travel. Each theory presents its own set of challenges and unanswered questions. The journey to faster-than-light travel is fraught with obstacles, but it is the pursuit of the impossible that often leads to the greatest discoveries. While faster-than-light travel remains a dream for now, who knows what the future might bring? In the realm of physics, nothing is ever truly impossible. So let's keep dreaming, let's keep exploring, and let's keep pushing the boundaries of what we believe is possible. As our cosmic voyage concludes, we trust you found this exploration into the intriguing realm of faster-than-light travel as enlightening as we did. From traversing the vast reaches of space-time to uncovering the enigmas of quantum entanglement and musing over the presence of elusive tachyons, we've continuously questioned our comprehension of the cosmos and its governing laws. Yet, this thrilling expedition is merely commencing, and we heartily invite you to accompany us in this pursuit of pushing the envelope of our beliefs. If this journey has taught you something new, do us a favor and hit the like button. Your contribution is vital in helping us produce more content that delves into the universe's mysteries. And remember, your opinions matter to us. Don't forget to share your thoughts on faster-than-light travel in the comments section. Do you deem it a possibility? Which theory has caught your fancy? Or maybe you have a query or a suggestion for an upcoming video. Let's keep this intellectual exchange. Don't forget to hit the subscribe button and the bell icon to update it with more such intriguing content. If you believe someone else would appreciate this exploration of space and time, do share this video with them. The quest for knowledge, after all, is best when embarked upon together. So let's continue to dream, discover, and challenge our beliefs collectively. As always, we appreciate your support. Until the next adventure, remember to keep your eyes on the stars.